Hello and welcome. I decided to return and make some new videos. So this is actually a first order differential equation from further maths. It's enrichment material. It's the start that is a little bit hard. The differential equation dy by dx is equal to y bracket y plus 1, and we have an ugly looking denominator y minus x xy minus 1, where y is a positive number, subject to the boundary condition x is 1 minus log 4 and y is equal to 1. If that is the case, to show that y plus the log of y plus 1 must be equal to 0. So the question is, where do we start with something like that? I mean, the obvious thing for something like that is perhaps to try for a substitution. What substitution? I mean, where do we start with something which looks as ugly as that? So what we're going to do is just tidy this up a little bit, first of all. Pardon me. And I'm talking about this particular denominator. So this, the numerator, we're going to leave as it is. And what we can do there is we can factorize perhaps in pairs. So y minus 1. So this is these two bits here. And if we pull an x, we're going to end up with 1 plus y. And why we're going to do something like that is because we can actually split the right hand side eventually. But we need to do something else first of all. In order to split it, I mean, that doesn't split. But if we were to bring that at the bottom, then we could. So all we're going to say therefore is dx by dy, flipping as a minus in there, is equal to y minus 1 minus x, y plus 1, and on the bottom we have y plus 1. I'm going to do it on the same line, so what we're going to end up with that is y minus 1 over y plus 1, and when we split this bit here, we're going to get minus x over y, which is not too bad. Again, we have to remember y is a positive quantity. Where do we go from there? Well, possibly where we can go from there, we'll make it a little bit neater, is to times the equation through by y. So we have dx by dy multiplied by y. This will get rid of that. So we have equal to y minus 1 over y plus 1 minus x. And perhaps the next thing, let's move this x to the other side. So we have y dx by dy plus another x is equal to y minus 1, y plus 1. Have we achieved anything by doing that? Because originally we did mention something about substitution. It's actually, we managed to achieve a standard first order differential equation, the one with the integrating factors. The only difference is the x and the y have swapped places. You remember the standard differential equation for something like this. What can we do? But let's write slightly different there. Perhaps divide the x again, sorry, the y again, just to actually so we can all see it. Dx by dy plus x over y is equal to y minus 1 over y plus 1. Now the standard differential equation, first order, the one with the integrating factors, is dy by dx plus, and then we have an normally in this particular case we will have a yf of x is equal to a g of x. If we look at what we have instead here, okay, is we have dx by dy plus, here it doesn't really matter what we've got, but it's an x now f of y. Our f of y is 1 over y is equal to a g of y. So basically things have actually swapped. Pardon me again. So we can do it either way. If we look at this particular quantity, we should spot that this is an exact differential d by dy of xy, because of course that will differentiate with respect to y, dx by dy times the y, which is this bit here, and then leave the first bit alone, which is x, differentiate the y with respect to y, which is 1, is equal to y minus 1 over y plus 1. Okay, if you didn't spot that, then we can actually do integrating factor. I'm going to just write it here on the side a little bit. So in order to do the integrating factor, first of all, remember that the differential operator must be on its own. So we're going to write it as dx by dy. All I'm doing in this particular line, I'm dividing the y through. So we have dx by dy plus x over y is just what I had actually written there. I regret rubbing it off. Y plus 1. And now remember, the integrating factor is with respect to y, so it's going to be equal to e, and is 1 over y dy, which of course is e to the log of y, which is y. So now if we multiply, this will make the left hand side exact, so we're going to have d by dy of xy is y times that, and of course if I multiply this by y, these things here will cancel, oops, and I end up with exactly the same thing. So the job is done either way. I mean, we should be able to see it. This is enrichment, by the way. It's a 5-star question, so we should be able to see all of this, that it's an exact equation. But if perhaps we can't quite see it, then we can always manipulate it. So what I'm going to do, let's make a little bit of space. So let's leave the original differential equation on the top. Let's take the very, very last line. And from here, it's actually quite straightforward. I mean, the 5 stars for this original manipulation, which is quite untied if you haven't seen anything like that before. So we're going to integrate both sides now. So with respect to y, so we have xy is equal to the integral of y minus 1 over y plus 1 with respect to y. How do we integrate something like this? I'm sorry, I'm not writing that. So this is equal to the integral now. Manipulate the integrand. I'm going to write it as y plus 1, and we need a minus 2 dy. Split the fraction now. So that's exactly the same instead of doing substitutions or anything else. So we have 1 minus 2 over y plus 1 dy. And now my xy is equal to, with respect to y, is going to be y minus 2 times the log of y plus 1 there. Since y is a positive number, I don't need moduli. Y plus 1 plus a constant, let's call it a. Make some more room again. And possibly put the boundary condition, I think, at this stage. So we're having y is equal to 1 there. So I'm looking on the left hand side. So x is 1 minus log 4 times 1, which is 1 minus log 4, is equal to 1 minus 2 log, y is 1 log 2 plus a. Log 4 and 2 log 2 is the same. 1 and 1 is the same. And therefore a must be 0. So we have got xy is equal to y minus 2 times the log of y plus 1. My handwriting is very, very bad these days. I have the shakes, probably due to some of the medication that I'm taking, just annoying me at times. So xy minus, okay, a is 0. And now this is a general solution, not general, sorry, the specific solution of the ODE. And it says, show that, oh, actually I didn't write that, it's quite bad of me. Show that y plus the log of y plus 1 is equal to 0 at x is equal to 3. I omitted that, I do apologize. So when x is equal to 3, we're having 3y is equal to y minus 2 times the log of, what do we have in there? Log of y plus 1. Let's move things to the other side. So we got minus 2, or no, actually minus plus 2y is equal to minus 2 log of y plus 1, or good, divide both sides by 2, and then move things to one side. Y plus the log of y plus 1 is equal to 0 as required. And this is the end of this particular differential. I hope you followed that initial step, which was not easy to see or apply if you haven't seen anything like that before. But hey, that's a 5-star enrichment question, and I'll try to make another one of these and put it up so it can give you a little bit of practice. For the time being, I'm signing out.